Every day, billions of people interact with artificial intelligence without even realizing it. Your phone's autocomplete, your streaming recommendations, the route your GPS selects, all powered by AI. But this technology didn't appear overnight. The story of AI spans 80 years, 2 world wars, multiple technological revolutions, and countless brilliant minds who refuse to give up on a seemingly impossible dream, creating machines that think. Welcome to Factopedia Tribe. Today, we're telling the complete story of artificial intelligence from secret wartime labs to the algorithms reshaping civilization itself. Our story begins not in a modern research lab, but in the desperate days of World War II. As Nazi Germany's Enigma machine encrypted military communications, Allied forces faced an impossible challenge: how do you decode messages when there are more possible combinations than atoms in the universe? Enter Alan Turing, a brilliant British mathematician who realized that to beat a machine, you needed a different kind of machine. His electromechanical computer at Bletchley Park didn't just crack codes, it demonstrated something revolutionary. Machines could perform logical operations, manipulate symbols, and in a sense, reason. But Turing saw further. In 1950, he published a paper asking a question that still echoes today: can machines think? His proposed test could make a machine converse so naturally that you couldn't distinguish it from a human, and set the stage for everything that followed. The problem? The computers of Turing's era were massive, expensive, and painfully slow. To make thinking machines practical, they'd need to get dramatically smaller and faster. That required an entirely new technology. The year was 1947. At Bell Laboratories in New Jersey, physicist William Shockley and his team invented something that would change everything: the transistor. This tiny device could amplify and switch electronic signals, doing the same job as bulky vacuum tubes but using a fraction of the space and power. Think of it this way: if computers were cars, vacuum tubes were steam engines, powerful but impractical. Transistors were the internal combustion engine, compact, reliable, and scalable. But Shockley's abrasive personality drove away his best researchers. In 1957, 8 of his top engineers, later called the Traitorous Eight, left to form their own company, Fairchild Semiconductor. This wasn't just a business decision, it was the birth of Silicon Valley itself. Among these rebels was Robert Noyce, who solved a critical problem: how do you connect thousands of transistors without thousands of wires? His answer, the integrated circuit, or microchip, packed multiple components onto a single piece of silicon. Now you could build complex circuits the size of your fingernail. His colleague Gordon Moore noticed something remarkable: the number of transistors you could fit on a chip seemed to double every year. This observation, later called Moore's Law, predicted that computing power would grow exponentially while costs plummeted. He was right, and that exponential curve is what eventually made AI possible. Meanwhile, engineer Gene Horney developed the planar process, a manufacturing technique that made it economical to mass-produce these chips. The pieces were falling into place. By the early 1970s, Intel engineer Ted Hoff faced a unique challenge. A Japanese calculator company called Bizicom needed custom chips for their products, but designing unique chips for each model was too expensive. Hoff's solution? Create one programmable chip, a microprocessor that could be reprogrammed for different tasks. The Intel 4004 was born, and with it, the personal computer revolution became inevitable. Suddenly, computing power wasn't just for governments and corporations. It was becoming accessible to everyone. And accessible computing meant accessible AI research. While engineers were building better chips, computer scientists were wrestling with a fundamental question: how do you program intelligence? In 1956, at a summer conference at Dartmouth College, computer scientist John McCarthy officially coined the term artificial intelligence. The researchers gathered there believed they could create thinking machines within a generation. They were spectacularly wrong about the timeline but right about the possibility. Early AI focused on symbolic reasoning, teaching computers to follow logical rules. This worked well for chess and mathematical proofs but failed miserably at things humans find easy like recognizing faces or understanding language. Why? Because these tasks don't follow simple rules. They require learning from experience. Enter neural networks, inspired by how the human brain processes information. Instead of following programmed rules, these networks could adjust their internal connections to learn patterns from data. In theory, you could show a neural network thousands of cat pictures, and it would learn to recognize cats without anyone explicitly programming cat rules. But there was a problem. Marvin Minsky, one of AI's founding figures, published research in the late 1960s showing mathematical limitations of simple neural networks. His critique was technically correct but created a psychological barrier. Funding dried up. Neural network research entered what's now called the AI winter decades, where the field was considered a dead end. While mainstream AI struggled, a Canadian professor named Geoffrey Hinton refused to give up on neural networks. Working in relative obscurity through the 1980s and 90s, Hinton developed new mathematical techniques for training deeper, more complex networks. The key insight? With enough data and computing power, neural networks could learn hierarchical representations, first detecting edges, then shapes, then objects, then concepts. But he needed proof. He needed a breakthrough that would force the world to pay attention. The internet changed everything. By the 2000s, billions of people were uploading photos, writing text, creating data at an unprecedented scale. For the first time in history, researchers had the massive datasets neural networks needed to learn. A Stanford professor named Fei-Fei Li recognized this opportunity. In 2009, she released ImageNet database of 14 million labeled images spanning 20,000 categories. She turned this into an annual competition, whose AI system could most accurately identify objects in images. For years, traditional computer vision techniques dominated. Then came 2012. Geoffrey Hinton and his graduate students, Alex Krashevsky and Ilya Sutskever, entered a deep neural network called AlexNet into the ImageNet competition. Their approach was different. Instead of hand-coding features for the AI to detect, they let the network learn features automatically from the data. They also leveraged powerful graphics processing units, GPUs originally designed for video games. AlexNet didn't just win. It obliterated the competition, cutting the error rate nearly in half. The AI winter was over. Deep learning had arrived. But there was still a hardware problem. Training these massive neural networks required enormous computational power. Enter Jensen Huang and NVIDIA. NVIDIA had built its business making graphics cards for gaming, but Huang recognized that the parallel processing power of GPUs was perfect for AI calculations. While traditional CPUs were like a single brilliant mathematician solving problems sequentially, GPUs were like thousands of average students working simultaneously, perfect for the matrix multiplications neural networks required. NVIDIA bet its future on AI, designing specialized chips for deep learning. Companies like Google, Microsoft, and Facebook began buying thousands of these GPUs, building massive data centers dedicated to AI research. AMD and Intel raced to catch up, but NVIDIA had a crucial head start. Meanwhile, tech giants were building AI systems that were already changing daily life. Google used neural networks to revolutionize image search and translation. IBM's Watson won Jeopardy! Against human champions. Smaller companies like Ward Systems developed accessible neural network software for businesses. Facebook used AI to identify faces and curate news feeds. The infrastructure was in place. The talent was mobilized. The stage was set for AI to move from research labs into everyday products. Then, in late 2022, everything accelerated. OpenAI, led by Sam Altman, released ChatGPT, a conversational AI that could write essays, debug code, and engage in nuanced discussions. Within 5 days, it had 1 million users. Within 2 months, 100 million. It was the fastest-growing consumer application in history. What made ChatGPT different? Previous AI systems were specialists' narrow tools designed for specific tasks. ChatGPT was a generalist, trained on vast swaths of internet text to understand and generate language about almost anything. It wasn't perfect, but it was accessible and useful enough to spark global fascination and concern. Simultaneously, AI image generators like Stable Diffusion developed by entrepreneur Ahmad Mostaque made it possible for anyone to create professional quality artwork from text descriptions. The barriers between imagination and creation were crumbling. This explosion of generative AI attracted massive investment. Tech visionaries like Peter Thiel and Reid Hoffman poured billions into AI startups. Elon Musk, despite co-founding OpenAI, launched competing AI ventures while warning about existential risks. The technology titans faced a dilemma. AI offered immense economic and social benefits, but also unprecedented challenges. Who owns the copyright to AI-generated art? How do we prevent AI from amplifying human biases? What happens to jobs when machines can do cognitive work? And could sufficiently advanced AI pose fundamental risks to humanity? Today, we stand at an inflection point. AI that seemed impossible a decade ago is now mundane. Systems like ChatGPT represent what researchers call narrow AI, highly capable within specific domains but lacking general intelligence or consciousness. The next frontier is what researchers call AGI, artificial general intelligence systems that can match or exceed human abilities across the full spectrum of cognitive tasks. Some experts predict this could happen within years, others think it's decades or centuries away. A few believe it may be impossible. What's certain is this: the story of AI is ultimately a story about us, our creativity, our ambition, our fears, and our hopes. Every breakthrough came from people who refused to accept that machines couldn't think, couldn't learn, couldn't create. From Alan Turing's wartime codebreaker to today's language models, from Shockley's transistor to NVIDIA's AI chips, from Minsky's skepticism to Hinton's persistence, each chapter in AI's history reminds us that the future isn't predetermined. It's built by people willing to imagine the impossible and work relentlessly to make it real. The question now isn't just, can machines think? It's, what kind of thinking machines do we want to create? And that's a question we all get to answer. This has been Factopedia Tribe. If you found this journey through AI history fascinating, hit that subscribe button. Drop a comment telling us, which AI breakthrough surprised you most? And what AI capabilities do you think we'll see in the next decade? See you in the next video.